Howdy. This video is on the intermolecular forces, London dispersion, induced dipole interaction, and dipole-dipole interaction. London dispersion is one of the most important intermolecular forces. Everything experiences London dispersion forces. Dipole-induced dipole interaction is why gases dissolve in water, and dipole-dipole interaction can sometimes dominate the situation. After watching this video, you should be able to describe each of these interactions, identify when they occur, and describe examples of them occurring and why those examples are important. Intramolecular forces are the forces that hold atoms together. They're the covalent bonds. Intermolecular forces are the forces between molecules, between ions, and between molecules and ions. Intermolecular forces are responsible for the physical properties. And so intermolecular forces determine boiling point, melting point, vapor pressure, solubility, viscosity, surface tension, and capillary action. And so the stronger the intermolecular attraction, the more kinetic energy is needed to overcome that intermolecular attraction, and hence the higher the melting point, higher the boiling point, and the lower the vapor pressure. And so you can imagine any phase transition as a competition between intermolecular attraction and kinetic energy. And you can think about temperature as a measure of kinetic energy at the atomic level. So all intermolecular forces are based on the electrostatic interaction. Electrostatic interaction is where opposite charged particles attract, like charged particles repel, and electrostatic interaction follows Coulomb's law, which says that the force is equal to K, a constant that we don't care about, times the charge in particle 1, charge in particle 2, divided by the distance between the particles squared. And so the bigger the charges, the stronger the interaction. The shorter the distance, the stronger the interaction. We saw previously that the electrostatic interaction determines energy levels of atomic orbitals, bonding of electrons, and lattice enthalpy. The stronger the attraction, the more stable the configuration. The stronger the repulsion, the less stable. And so all intermolecular forces are based on electrostatic interaction. And so we can understand their relative energies by thinking about Coulomb's law. And so for ion-ion interaction, you have full charges. And so that's going to give you a fairly strong energy. If you're talking about dipole-dipole, those are just partial charges, and so the energy is much smaller. Induced dipole is also referred to as London dispersion. I'll use those two terms interchangeably. Hydrogen bonding is a form of dipole-dipole interaction, but it's an especially strong form of dipole-dipole. And so hydrogen bonding is an order of magnitude stronger than regular dipole-dipole interaction. Notice that regular dipole-dipole interaction has similar energy as London dispersion. And so the ion-ion interaction occurs when you have ions like an ionic solid. Whenever you see dipole, think polar molecule. And so the ion-dipole interaction occurs when you have an ion and a polar molecule. So you can imagine if you have an ion dissolved in water, you're going to have the ion-dipole interaction. Dipole-dipole interaction is the interaction between two polar molecules. Again, when you see dipole, think polar molecule. Dipole-induced dipole is when a polar molecule induces a dipole moment in another molecule, typically a dipolar molecule. And then induced dipole, you can imagine as between two nonpolar molecules, but again, everything has induced dipole. And so to know what the interaction present, we have to be able to recognize ionic solids and molecules, be able to determine if a molecule is polar or nonpolar. And so we have to be also know what the molecular shape of the molecule is. And so when asked about the boiling point, melting point, vapor pressure, viscosity, surface tension, etc., first we have to determine what is the dominant interaction for each compound. And you need to know the relative strength of the different intermolecular forces. And so again, remember ion-ion is the strongest, then ion-dipole, dipole-dipole. Hydrogen bonding is above dipole-dipole, dipole-induced dipole, then induced dipole. Now, if we talk about induced dipole, again, which is also referred as London dispersion, one thing we should notice is that it's easiest to polarize a molecule. The easier to polarize a molecule, the stronger the London dispersion. And the more massive the molecule, the easier to polarize, hence the stronger the London dispersion interaction. And so each of these interactions depends on different things. For London dispersion, the more massive, the easier to polarize, the stronger the London dispersion interaction.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules.
And so when you bring two molecules together that are nonpolar, they can distort each other's electron cloud and become slightly polar. So that's what we mean by induced dipole interaction. And again, for London dispersion, the more massive the molecule, the easier to polarize, the stronger the attraction, hence the higher the melting point, higher the boiling point, and the lower the vapor pressure. Now this actually gives you a plot of the energy versus the distance for two argon atoms. Now argon atoms aren't going to form a bond, but what we can see is that as they come closer, the energy actually goes down. And so they're inducing a dipole moment in each other. If they get too close, then you start getting the electrostatic repulsion. So the higher the molecular weight, the easier to polarize, the stronger the London dispersion. Now for hydrocarbons, molecules composed of just hydrogen and carbon, because the difference electronegativities between carbon and hydrogen is 0.4, and carbon never has a lone pair, hydrocarbons are nonpolar. And so the only interaction that they have is London dispersion. And so what we notice is that the heavier the hydrocarbon, the higher the boiling point. Again, higher molecular weight, easier to polarize, stronger London dispersion, higher boiling point, higher melting point, and the lower the vapor pressure. It's a coincidence, though, that this relationship is linear. And so here's a longer list of hydrocarbons and their boiling points. And again, the larger the molar mass, the stronger London dispersion, and hence the higher the boiling point. It's kind of interesting. For the first four, they're gases at room temperature, and then the next five are liquids at room temperature. Now, so the most important consideration for London dispersion is the molar mass. The more massive, the easier to polarize, the stronger the London dispersion. A secondary consideration is actually the shape of the molecule. And so you can imagine that if you have more surface area of the molecule, there's more area for the two molecules to interact, and that will give you a slightly stronger London dispersion interaction. If you have less surface area of interaction, then it's going to be a little bit weaker London dispersion. And so if you have a branched alkane, that's a little bit more spherical-like, and so you'd expect that these would have a weaker interaction and a lower boiling point than if you have a long chain alkane, which has larger surface area. And so here are some structural isomers for C6H14. And this one, you have the long chain, so you're going to have more surface area. It has a boiling point of 69. Here we have a little bit of branching. Again, all five of these have exactly the same number and type of atoms. A little bit of branching, and the boiling point goes down to 63 or 60. More branching, and the boiling point goes down to 58 and 50. And so for London dispersion, most important consideration is the molar mass. The larger the molar mass, the easier to polarize, the stronger the interaction. A secondary consideration is the more surface area of the molecule, the stronger the interaction, the higher the boiling point. So for dipole-induced dipole, that's when you have a molecule that is polar interacting with a molecule that is not polar. And so we saw that two nonpolar molecules can induce a dipole moment in each other. And so a polar molecule can induce a dipole moment in a nonpolar molecule. And so the more mass of the nonpolar molecule, the easier it is to polarize, the stronger electrostatic attraction, and hence the stronger the dipole-induced dipole interaction. And in the case of where you have a nonpolar molecule dissolving in water, the more mass the molecule is polarized, the more soluble the nonpolar molecule is in water.
On average, the electron cloud of an O2 molecule is distributed symmetrically across the molecule. The molecule is not polar. A water molecule, which is polar, repels the electron cloud, causing it to be asymmetrically distributed and thereby induces a dipole in the O2. This shift allows O2 to be weakly attracted to the water molecule.
And so if it wasn't for this attraction between nonpolar molecules and water, there would be no gases dissolved in water. And so Henry's law says that at constant temperature, the solubility of the gas is directly proportional to the pressure of the gas above the solution. And solubility of the gas is equal to Henry's constant times the partial pressure of the gas above the solution. Now the KH actually depends on which gas you're looking at. And so if we look at a graph here, we have solubility in the liquid as a function of pressure. And so you have O2, N2, and helium. And so of these, O2 is the most massive, so it should be easiest to polarize. And so it's the most soluble of these three. And helium is the smallest, least easy to polarize, is the least soluble in water. We can look at a lot bigger table. And again, the larger the molecule, easier to polarize, more soluble in water. And then finally, we can talk about dipole-dipole interaction, which you can think about as just a polar molecule interacting with a polar molecule. And so the difference in the electronegativity of hydrogen and chlorine is greater than 0.5. So both of these molecules are polar. Chlorine's more electronegative, so it has a partial negative charge. And so you have an interaction between the partial negative end of the chlorine and the partial positive end of the hydrogen. Now again, hydrogen bonding is a especially strong form of dipole-dipole interaction. And so difference electronegativity here is 0.8. Remember, if the difference electronegativity is between 0.5 and 2, we consider that polar covalent.
Hydrogen chloride molecules are polar. When HCl molecules in the gas phase are cooled, the kinetic energy of the molecules can no longer overcome the dipole-dipole forces between them. The opposite ends of the molecules attract each other and coalesce to form a liquid.
And so if two molecules are about the same size, and one has a dipole moment and the other one does not, the one with the dipole moment should have a higher boiling point. Now the reason that having the same size is important is because, again, London dispersion depends mostly on the molecular weight. And so here we have N2 and HF. You have 28 grams per mole and 20 grams per mole, so that's similar. And so we can assume that the London dispersion is about the same. Now HF is a lot more polar than N2, and so because HF is more polar than N2, we actually get a higher boiling point. HF actually has hydrogen bonding. Now here I have Br2 ICl, very similar molar masses. ICl is a little bit polar, and so it's going to have a higher boiling point. And so dipole-dipole is only really going to become important if you have molecules that have about the same molecular weight, meaning that they have the same London dispersion. And so polar molecules have higher boiling points and melting points and lower vapor pressures than nonpolar molecules of about the same size. Again, because London dispersion depends on the molar mass. When they have about the same size, and if one has a dipole moment, the other one does not, the one with the dipole moment will have a higher boiling point, higher melting point, and a lower vapor pressure. And so for polar molecules, the more polar the molecule, the stronger the attraction, higher melting point, higher boiling point, lower vapor pressure. For nonpolar molecules, the more massive, easier to polarize, stronger electrostatic attraction, higher melting point, higher boiling point, and lower vapor pressure. Now this plot is really kind of interesting. And so in blue is the dipole moment. And so it's a measure of how polar a molecule is. The gold is a measure of the boiling point. And so you can say that in general, as the blue goes up, the boiling point goes up. Again, the more polar the molecule, the stronger the interaction, the higher the boiling point, melting point, and the lower the vapor pressure. Now for these at the bottom here, even though the dipole moment isn't that big, the boiling point's about the same. And the reason for that is that these last two have fairly large molar masses. And so it's probably London dispersion that's the dominant interaction for these three. And if they have the similar molar mass, which they do, that explains that it's due to London dispersion. And so a question you could see would be put the following in order of increasing boiling point. And so you have xenon, neon, and krypton. Neon and krypton. So first you have to determine what's the intermolecular forces that are important. Now these are all noble gases, and so they're single atoms floating around, and so the only intermolecular force that's present is going to be London dispersion. And we've seen that for London dispersion, the larger the molar mass, the easier it is to polarize, the stronger the London forces, and higher melting point, higher boiling point, and lower vapor pressure. And so xenon has the highest molar mass, it should have the highest boiling point. Neon has the lowest molar mass, should have the lowest boiling point. Put the following in order of increasing melting point. So we have CH4, CF4, and CCl4. And so again, the first thing I have to do is determine what are the intermolecular forces that are important. Now, we should be able to draw these Lewis diagrams, and we see that for all three of these, we have a center atom surrounded by the same type of outer atoms with no lone pairs at the center, and so they're all nonpolar. And so again, the only interaction is London dispersion. And again, for London dispersion, the larger the molar mass, the easier to polarize, the stronger London dispersion, higher melting point, higher boiling point, lower vapor pressure. And so the carbon tetrachloride has the largest molar mass, will have the highest boiling point, and the methane will have the smallest molar mass and the lowest boiling point. Which has higher vapor pressure, BCl3 or BF3? So again, first you have to determine what are the intermolecular forces that are important. So are these polar or nonpolar? And so if we draw the Lewis diagram, we see again that we have a center atom surrounded by the same type of outer atoms. And so they're both nonpolar. The only interaction is London dispersion. Their corresponding boiling points will be 12.5 and minus 100. And so BCl3 should have the strongest interaction, and that will give it the highest boiling point, highest melting point, and the lowest vapor pressure. And so BF3 should have the higher vapor pressure, which has a higher boiling point, O2 or O3. And so again, we have to figure out, what is the interactions present. So we should draw the Lewis diagram. Often we have to determine electron geometry, molecular structure, and determine whether or not the molecule is polar or nonpolar. And so we can draw Lewis diagrams. And so for O2, it's pretty simple. We just have two oxygen atoms with a double bond. For ozone, we have two resonant structures, and it's going to give us trigonal planar. Now remember, if you cannot prove that it's nonpolar, it's probably a little polar. And so for O2, that has to be nonpolar. For ozone, that probably can be a little bit polar, right? Even though these bonds are polar, doesn't mean the molecule's not polar. So it's probably a little polar. And so for O2, you have just London dispersion. For ozone, you have London dispersion and dipole-dipole interaction. Now for ozone, your London dispersion is going to be greater than O2 because it's more massive. And so the boiling point for ozone should be bigger than the boiling point for O2. So which has a higher boiling point, PF5 or SF4? So again, you have to determine, what's the intermolecular forces present? Are these molecules polar or nonpolar? And so for PF5, you have trigonal bipyramidal molecular shape and electron geometry. For sulfur tetrafluoride, you have trigonal bipyramidal electron geometry and seesaw molecular shape. Now we can prove that PF5 is nonpolar because we have a center atom surrounded by the same type of atoms with no lone pairs, so this one has to be nonpolar. We can't do the same thing with sulfur tetrafluoride, and so that's probably a little bit polar. And so the sulfur tetrafluoride would expect to have a little bit higher boiling point. We can do the same thing with sulfur hexafluoride versus chlorine pentafluoride. And so we have to determine, are these polar or nonpolar? What are the intermolecular forces present? So if sulfur hexafluoride has an octahedral electron geometry, octahedral molecular shape, it's got to be nonpolar. Chlorine pentafluoride is octahedral electron geometry and square pyramidal molecular shape. Now we can prove that SF6 has to be nonpolar, but ClF5 could be a little bit polar, and so we'd expect that the ClF5, the chlorine pentafluoride, probably has a little bit higher boiling point. So all intermolecular forces are electrostatic interactions, and so we can understand the relative energy of the different intermolecular forces based on Coulomb's law. The bigger the charges, the stronger interaction. And so with ion-ion, you're dealing with full charges, plus ones, minus ones, plus two, minus two. For dipole, you're just dealing with a partial charge. And again, the physical properties are determined by the intermolecular forces. For instance, the stronger intermolecular forces, the higher the melting point, higher the boiling point, and the lower the vapor pressure. I hope that was helpful.